single loop circuits, and more specifically, voltage division. So I got a lot of stuff on this piece of paper, so we're going to kind of go through it bit by bit. If you get anything out of this, thumbs up, subscribe, share, tell me what you like, tell me what you don't like. Voltage division, single loop circuits, this is really important. So we're going to be talking about things that are in series. So if we look over here, this is a voltage source and two resistors. This is all just one loop or one wire. So they are in series together. So anytime you have anything in series, the current is the same in all elements. That's important for series. Always remember that. When something is in series, they have the same current. The voltage is going to change. And you're going to solve these types of circuits with KVL. Link up top. Watch it if you haven't. It's good stuff. All right, so let's pull this down. So with that said, we know that these resistors, R1 and R2, are going to have a voltage drop. And those voltage drops are going to be equal to VR1 and VR2. And we know that whatever the value of VR1 is and whatever the value of VR2 is, they have to sum to the value of V of t. All right, so and here's that. VR1 plus VR2 is going to be negative V of t equals 0. VR1 plus VR2 equals V of t. From Ohm's law, V equals IR, we know that VR1, so the voltage in R1, is going to equal the resistance of R1 times the current. So R1 times I of t, same thing goes for VR2. VR2 is just going to equal whatever the resistance of R2 is, multiplied by that current going through them. So VR2 equals R2 times I of t. Nothing crazy there. All right, this is where it gets a little bit in the weeds. Skip ahead if you just kind of want to see the meat and potatoes of solving voltage division. But let's kind of go through the math of what's going on here. So with that, we know that V of t is going to equal, because we're going to take this equation here and apply it here. So V of t is going to equal VR1 plus VR2, but we know that those equal R1 times I of t plus R2 times I of t. All I did was take these values and plug them in. That's it. All right, so now we're going to factor out I of t. So we have V of t equals I of t times R1 plus R2. All I did was take that I of t that's here, bring it to the outside. That's it. Now we solve for I of t. That's just simply V of t divided by R1 plus R2. You get I of t. I of t equals V of t over R1 plus R2. Now with that, that's a very complicated way of saying we now have a current. Because all you're doing when you find current, you're just going to take your total resistance and use that in Ohm's law. Pretty simple. So now we're going to use Ohm's law to find voltage across each resistor. All right, so this second page basically just has what we already did. We have VR1 equals R1 times I of t. VR2 equals R2 times I of t. Again, that's just the voltage across those resistors R1 and R2. But we're going to take our equation I of t and plug it in here. So VR1 is now going to equal R1 times V of t over R1 plus R2, and we're going to do the same thing on this side as well. So to write that a little bit more simply, your voltage across resistor 1 equals R1 over R1 plus R2 times your voltage source. Same thing goes for VR2. Voltage across R2 is R2 over R1 plus R2. So notice something. When we're looking for our voltage across R1, resistor R1 is in your numerator here. It's resistor R1 divided by R1 plus R2. When you're looking for the voltage across resistor 2, resistor number 2 is in the numerator. And it's divided by R1 plus R2, multiplied by your source. And that is a voltage divider, which the voltage divider I wrote out is just as the source voltage is proportionally divided between the resistors. The bigger the resistor, the bigger its voltage drop. The smaller the resistor, smaller the voltage drop. All right, so now that I got some of that information moved up out the way, this right here, this is the real meat and potatoes of what we need. All right, so now let's use that information to solve this problem. So let's say we have a 9-volt source. We have our current I going in a clockwise direction. R1 is going to equal 90 ohms. R2 is going to equal 30 ohms. Let's find the voltage drop across R1 and R2. I also wrote out this V2 here just as something to see. You're going to see this in books. This comes out, got a low node. This comes out, it's got a low node. Pretend that that's like a multimeter right there and calling it voltage 2. I just wanted that just for the aesthetics. Learn what it is here, so when you see it on a test or in a book or a homework assignment, it doesn't throw you. All right, so first let's solve for VR1. So VR1 is going to equal whatever R1 is over R1 plus R2 times our voltage source. So VR1 is going to equal 90 ohms. R1 plus R2, that's 30 plus 90, which is 120. All right, see that the ohms will cancel. Multiply by our source, which is 9 volts. So VR1 equals 90 divided by 120 is 0.75 times 9 volts. That's going to equal 6.75 volts. Now let's do VR2. So we're looking for voltage across R2. So that means we want its resistance, which is 30 ohms, over R1 plus R2, 120 ohms, multiply by our 9 volts. 30 divided by 120, that's just 0.25, so 0.25 times 9 volts is 2.25 volts. So that's going to be your voltage across each resistor. VR2, 2.25 volts. VR1, 6.75 volts. Now let's see if that makes sense. So R1 is bigger, so it should be getting rid of more voltage than R2. It's getting rid of 6.75 as opposed to R2, which is the smaller resistor, is only getting rid of 2.25 volts. So that makes sense. Now let's do sanity check number 2. These should add to 9 volts, which is KVL, Kirchhoff's voltage law. That loop, it all has to sum up to 0. In other words, R1 plus R2 needs to equal 9 volts. So 2.25 plus 6.75 does in fact equal 9, which means we're on the right track. All right, so I hope that was helpful. Hope you got something out of that voltage division little tutorial. And I hope you have a great day.